All right, so thanks to the organizers for the invitation. And what I'm going to talk about here is jets and differential operators in non-commutative geometry. So if you're not familiar with jets in classical differential geometry, they are a way of encoding the differential information for functions between manifolds, or what we'll care about here, sections of vector bundles. So generalizing that notion of jet. You could think of them in that setting as a sort of coordinate-free version of a Taylor series for a section of a vector bundle. But they're a way of encoding or treating differential operators. So differential operators will be maps out of jet bundles. And you can even treat differential equations in terms of jets. So there's this geometric theory of differential equations, which views linear differential equations as subbundles of jet bundles. And so this is a theory which we would like to generalize to the non-commutative setting. And you don't need a metric or a connection or anything classically to get jets. All you really need is the smooth structure, and you can construct your jets. So here, the analog, what we need in order to build a notion of jet is a first order calculus for most of the constructions. And sometimes the constructions will depend on higher degrees of your exterior algebra. And these are both notions we've come across in the earlier talks today. So a first order calculus, I won't really focus on this much, but let's look at an exterior algebra. So this is just the DGA, which is generated in degree 0. You can always truncate it and get a first order calculus. And if you have a first order calculus, you can always construct an exterior algebra, in particular the maximal exterior algebra, just by taking the tensor algebra and then quotienting by the minimal relations in order to get d squared to equal 0. Other exterior algebras will just be some further quotient of the maximal. And an exterior algebra you think of as some sort of non-commutative generalization as the de Rham complex, so some sort of generalization of forms. So these things would be anti-symmetric in a sense. So you can ask what would the corresponding notion of symmetric forms be? And there's a few possible definitions. The one I'll talk about here is the sort of inductive definition. There's other ones which will coincide in the case that the first degree of your exterior algebra, so omega 1, is flat as a right A module. So this is usually satisfied in examples that people would care about, right? If you're in the quantum group setting and you're dealing with calculi which are finitely generated projective, that's of course flat. So these things are satisfied. So your 0 degree symmetric forms, okay, and everything here is done at the functor level. So if you view the nth degree of your exterior algebra as a tensor functor, then you can build up your functors of quantum symmetric forms in this way. So you would think of, for the 0 and the 1 degree, they're pretty simple. For degree 2, S2 is just the inclusion into omega 1. Now they're tensor functors, so I'll write as a composition with omega 1. And then the wedge, this can be viewed as a natural transformation between these tensor functors. And the kernel of this would be what we define to be S2. And then you build up other things inductively. So the reason you would want this, or at least why we'll need this later, is for a notion of Spencer cohomology. So in this geometric theory of differential equations, you can consider the Spencer complex or the Spencer delta complex. These are two closely related complexes. And studying the cohomology of the Spencer delta complex for some linear differential equation will tell you things about formal integrability and solutions to your linear differential equation. What we have here would be the non-commutative analog of the Spencer delta complex for the empty differential equation. So classically, this will have vanishing cohomology, but in the non-commutative setting, this is not necessarily true. If you work with the maximal exterior algebra, we would conjecture that this Spencer cohomology for this sequence vanishes, and in all the examples we've looked at, it does, but we haven't quite proved that. So it's something you have to check for some example. And the way you build this up is using the maps which you use to inductively construct these quantum symmetric forms. And calling them quantum symmetric forms is maybe something of a misnomer. It doesn't have anything to do with quantum groups. It's just trying to indicate it's not symmetric in the classical sense of symmetric. It's some more general notion of symmetric. So how do you build jets? The first thing you would do is you would build the universal one jet, and then you try and construct a one jet for a non-universal calculus, and then you'll go to higher levels. So the universal calculus, this is just the kernel of the multiplication from a tensor A to A, where A is your K algebra. And this has the differential as stated there. And this short exact sequence here is what we would call the one jet short exact sequence for the universal calculus. And it comes with, well, the multiplication here. This would play the role of the one jet projection. And you have a splitting in the category of right A modules, which we would call the universal one jet prolongation. And there's some reasons which I won't go into for why you would consider this to be the reasonable object to take, but you want these things to, you want the corresponding notion of differential operators, which we'll get to later, to generalize the classical notion of differential operator, the classical notion of jet, and or even the Grothendieck notion of differential operator, if you just want to work with an algebra and not generalize things from the classical differential geometric setting. So this would be the starting point. Then you can do this for some universal calculus. So here, any differential calculus can always be viewed as some quotient of the universal calculus, right? And what we care about is this kernel here. So why we call it this, maybe this will become clearer later, but we would call this the functor of first order differential relations, or it will become a functor. For now, it's just a module, bimodule rather. And since omega 1d is a quotient of omega 1u by nd, you can use that sequence related to this sequence. So if you view nd including in here, and you can consider, well, there's an isomorphism with nd sitting here. You consider the co-kernel short exact sequence here. You use a snake lemma. You end up with a corresponding short exact sequence where the object in the middle is of this form. And this is what we would call the one jet for your differential calculus, omega 1d. And it satisfies a number of properties which are nice in the classical setting, which you would hope would carry through. One being that splittings of the one jet short exact sequence correspond, they're in bijective correspondence with left connections. But there are other reasons and other constructions that will sort of realize this in a more natural way. I just want the abbreviated version here to get to the notion of one jet. This comes with a notion of prolongation, so some map from E to J1E, or if you want to view it functorially, from the identity functor to this one jet functor, and a projection map, which both this prolongation and this projection will be natural transformations. And you get these, they're inherited from the universal prolongation and the universal projection. Just the slide there. Okay, so classically, you have a lot of different jets. Mostly you would come across holonomic jets, and these are usually just called jet functors or jet bundles in the bundle case. But the way you build them, so going back to Erzman, and then some of his students and other people started with, there's this notion of non-holonomic jet functor. So this is just iterated application of the one jet. I apply the one jet functor to the one jet functor to the one jet functor and so on. But this has a lot of redundant information, and you need to forget some of this. And the first step in forgetting this redundant information is equalizing these numerous jet projections that you now have. And when you equalize these jet projections, you get what are called the semiholonomic jet functors. And these already play a role classically. So there's an annals paper of Chap-Slovak and Suchek from 2001, where they're dealing with BGG sequences. And because they're dealing with parabolic geometries which have torsion, they can't work with holonomic jets. They have to work with semiholonomic jets. This is somewhat hidden in their paper, but there are reasons even classically why you would need to consider semiholonomic jets. Those are both pretty easy to construct. Holonomic jets, there's a bit more work that goes into constructing them, and we build them up inductively. And all of these have natural transformations, which play the role of prolongation, and projections, which are also natural transformations. I'll try to just talk about these holonomic jet functors. Go ahead. Intuitively, there's some way to say it. It has to do with, if you think of jets as giving some, like the k-jet of a section of a vector bundle, giving the kth order approximation of that section. You think of this as some sort of kth order neighborhood around your point, and it has to do with sort of, you can do that in terms of taking iterated first order infinitesimals, and you have to do this in a path independent way. So if I take sort of multiple infinitesimal paths to the same point, it has to somehow not see this path. This is very hand wavy here. Okay, so to construct the two jets, you can do it explicitly. You want it to be essentially generated by things which are generated by sums of things in S2, so these quantum symmetric two forms, and prolongations, second order prolongations, and then non-holonomic two jet. And that will coincide with this more implicit description as the kernel of a certain map from the non-holonomic two jet to this space here, which as a right module is just a direct sum, but as a left module, it has some more complicated action. And this sort of perspective on jets as a kernel of some map was already seen by Spencer and Goldschmidt in the 60s and 80s, or 60s and 70s when they were first looking at these things, but they never really explicitly said what this space was. But if you play around, you can sort of see what it is. This will turn out to be a lift of a differential operator. So you could call this a formal differential operator. So you can, in the end, see the two jets as a solution to a first order differential equation on the one jet, or sorry, a solution to the first order differential operator on the one jet. Or we'll see later, you can view it as some sort of first order linear differential equation. And this will restrict in the classical case to the classical two jet. Then there's ways to build up higher jets. You can build them inductively. You can build them also via pullback. There's a few different definitions, but they will coincide in the case that you, again, have your first degree of your exterior algebra, so omega 1D, your first order calculus, being flat as a right A module. And flat, I just mean the corresponding tensor functor is exact. It takes short exact sequences to short exact sequences. So you build them inductively. I won't go into many details. But then one property you want is that this jet short exact sequence holds. And the reason you would want this is differential operators. Classically, you would try and characterize them in terms of their symbols. And so a differential operator will be some map out of, like an nth order differential operator will correspond to a map out of an n jet. And if you restrict that map to these quantum symmetric forms, that would be what's called the symbol. So for instance, connections are first order differential operators whose symbol is the identity map. And so there's reasons why you want this sequence to hold, but in order to get it to hold, you need this Spencer cohomology to vanish, which classically always does, but again, in this noncommutative setting, you need to check that your Spencer cohomology vanishes. And for this sequence to be short exact in general, you also need omega 1, omega 2, and omega 3 to be flat as right A modules. So what is a differential operator? I sort of gave a sketchy definition before, but this would be a k-linear map between A modules, and you want it to factor through the jet prolongation by some A-linear map. So this is k-linear, and you need there to exist some A-linear map such that this diagram commutes. And then you would say this is some linear differential operator of order at most n. And a linear differential operator of order at most n will also be a differential operator of order at most m, where m is greater than n. If n is minimal, you'd say it's order precisely n. And this is exactly the same as what you would define things to be in the classical setting. So what are examples of these things? So the differential is itself a differential operator. Left connections. If your calculus is free and finally generated, so you'd call this parallelizable, then partial derivatives are differential operators. This map that we looked at before, if you look at its lift, so it turns out to be a differential operator, its lift, the kernel of that will be the two jet. We have a notion of vector field. So this would be a differential operator of order at most 1 from the algebra to itself, which annihilates the kernel of D. So classically, the kernel of D is locally constant functions. And so this, at least to us, was the most reasonable definition of a vector field. And we actually get a bimodule isomorphism with the existing notion of left vector field. And sometimes you want to think of your vector fields as duals to one form. Sometimes you want to think of them as differential operators from your algebra to itself. So it helps to have both definitions around. Our definition is nicer if you want to compose things, right? If you want to compose a differential operator from A to A with another one, now you can nicely. And with this notion of vector field, there's also, if a certain map exists, a notion of Lie bracket. So you need a certain map from vector fields, tensor vector fields to a different space, which I won't go into. If this map exists, you get a notion of Lie bracket. So you get a way to take two vector fields and get a new vector field out. And if you do this for triangular Hopf algebras, for using the calculus arising from the braiding, then our vector fields will correspond to the braided derivations, and the bracket that we get in our way will correspond to the braided commutator. There's other examples where you can do this, for instance, for any calculus on a group algebra for a finite group, or any differential calculus for a Clifford algebra. There's a canonical way to get a Lie bracket out of that. And we're looking at, yes. So differential operators, you can compose them. This is obviously something that you want differential operators to satisfy. And in order to see this, you take two differential operators. They both have lifts, and you need a lift of the composition. And so that involves constructing this map here. So you need a map from Jm plus n to Jm of Jn. And it's a bit of work to construct this, but once you have that, this composition will be a lift of the differential operator. So then you get some category of finite order differential operators. And so the objects there are the same as the objects in A mod, so left A modules, and the morphisms are finite order differential operators. You can do this with the infinite jet as well, and infinite order differential operators. We'll get to that at the end. So another thing that you want to hold classically is you want jets to represent differential operators. So you want, well, let's say lifts of differential operators to be in, maybe I'll go back to the diagram here. So classically, you have that maps of this form are in bijective correspondence with maps here. In the non-commutative setting, this isn't true. This is something which you have to check whether your example or class of examples satisfies this. In general, there will be multiple lifts of the same differential operator. So, yeah, so when is this functor here? We want to know when differential operators of order at most n is represented by some object. And well, we want it to be represented by the n jet. So when is this true? For this, you have to look at this natural transformation, which you always have from the universal one jet, so just this tensor functor, to the n jet. And on objects, this sends a tensor e to a times this n jet prolongation of e. And the kernel of this is, we would call these differential relations of order n. So these are submodules of the kernel of the map from the universal one jet to, from the universal differential calculus to your choice of calculus. And so these higher order differential relations are submodules of ND, which was the kernel of the map from omega 1u to omega 1d. So this is, you end up with a sort of tower of these differential relations. And so you have n, this will include into n2 and include into n1, this will include into your universal. So you have this tower, smaller and smaller sub bimodules of omega 1u. And it turns out what you need for jets to represent differential operators is for your jets to be quotients of the universal one jet by these higher order differential relations. So you need them to be quotients of this if you want jets to be representative objects for differential operators. But you could equivalently see this as these quantum symmetric forms being generated by prolongations. Classically, I mean, jets always represent differential operators, so perhaps this perspective wasn't known classically because there's no differentiation between these things, but it's somewhat surprising from the classical perspective that this is required. It wasn't even known that jets were generated by prolongations classically, although we found that to be the case. So if you want jets to represent differential operators, one way you can see this is if your quantum symmetric forms are a quotient of these higher order differential relations. Another way is just you need your jets to coincide with what we would call skeletal jets. Skeletal because they're somehow the minimal possible object, which could possibly play the role of a jet. It's the image of this natural transformation we saw on 2 slides previously. So it's precisely generated by prolongations, and it sits inside, it's a sub-object of the n-jet. So 0 order jets, these always represent 0 order differential operators. That's trivial. For 1 jets, this is always the case. For 2 jets, if you want your 2 jet to represent differential operators, you need to be working with the maximal exterior algebra. So this is some sort of, if you want your jets to behave, at least in this respect, like they do classically, you would need to be working with the maximal exterior algebra. And in general, if you want jets to represent differential operators, you need your jets to be skeletal in this sense, so generated by prolongations. Okay, so what I mostly wanted to talk about is this last few slides here. So the infinity jet, this is the same construction as you would find classically. You have this tower of jet functors and the jet projection, which these are natural transformations between these jet functors. You take the limit of this, so the projective limit, and you call this the infinity jet. And this has what's called a comonad structure on it. So first, let's say if you take an element of the infinity jet, this is going to be some sequence. So this is going to be some element of J0 of E, so just E. This is some element of J1 of E. This is some element of Jn of E. And since your infinity jet is some projective limit, you have some cone over that tower we saw before, and these have to be compatible with the projection. So if I project this down to some lower element in this sequence, it gives precisely that element. So if I project En hat down to Ek hat, I get precisely Ek hat. And if I truncate these sequences, so if I forget the first K elements here, I'll denote this by Ek. So this jet comonad, this is necessary in order to compose infinite order differential operators. So the map, which was called L before, if I go back here, so to this diagram, if I want to compose infinite order differential operators, I no longer have this map here. What I need is some sort of comonad, which is compatible with the infinite jet prolongations. And then you can compose infinite order differential operators. And this is precisely the map which allows you to do this. So you take some element of J infinity, which is a sequence of this form, and you send it to this sequence of sequences. This would be the comultiplication for your comonad. And this, so sending some sequence to the 0th element is the co-unit for this comonad. And in order to prove this, I mean, the hard part is checking that this actually lives in J infinity of J infinity, and then you just check co-unitality and co-associativity. And one of the points of having this comonad structure is it gives you a notion of differential equation. So this is the last slide here. First, maybe I'll mention there's several ways which you can now use this to get some sort of non-commutative generalization of a notion of PDE. So one would be via D modules. So D, this is just the algebra of differential operators from A to itself, which is, it's an algebra under composition, and you can consider modules for that. These would correspond to linear differential equations, right? This is sort of the algebraic geometric approach to linear PDE. D algebras then would be monoids in the category of D modules, and this would give you some notion of polynomial nonlinear differential equation. We haven't explored this much, but there are other notions of differential equations, so a more classical differential geometric approach would be this geometric theory of differential equations. So Spencer, Quillen, Goldschmidt, they sort of developed this theory, and this is where you consider some monomorphism into so in the classical case, into a jet bundle. So you consider some sub-bundle of a jet bundle. This would be a linear differential equation. And then you might ask that it be formally integrable. So if you prolong it and then project back down, this has to be a surjective map. You would ask that the prolongation is also a sub-bundle of some higher jet bundle. And then you can study this Spencer cohomology on these differential equations, and they tell you things about solutions, when solutions exist, and so on. And so we're sort of trying to replicate this theory. But the one which automatically works right now is this jet comonad approach to PDE. So this is, if you're familiar with Vinogradov's category of differential equations, this is a category whose objects are diffides, which are infinite prolongations of differential equations, together with Cartan distribution, which is something which essentially encodes the solutions of the differential equation. And the morphisms there are Cartan distribution preserving morphisms between these diffides. And one of his students, Marvan, had realized in the 80s that if you restrict Vinogradov's category of differential equations to a fixed base manifold, that it's equivalent to the Eilenberg-Moore category for the jet comonad. So he was the first one to note that the infinity jet classically has a comonad structure. And if you consider its Eilenberg-Moore category, that happens to be equivalent to this category of differential equations. And later, so 2017, Schreiber and Kalkin, they extended this to the synthetic differential geometric setting. So you're working in topos models of synthetic differential geometry, right? These are topoi into which the category of smooth manifolds embeds faithfully. And so you're allowed to work with infinitesimals in some rigorous fashion. There they also get that their infinity jet is a comonad. And so they get some category of differential equations as well. This works in our setting. So if you use this sort of definition of linear differential equation, in order to get it to be a coalgebra for the jet comonad, so to be an object in the Eilenberg-Moore category, you need omega-1 and omega-2 to be flat as right A modules. And going the other way, you need no conditions in order to get coalgebras for the jet comonad to be differential equations in this sense. So if you're willing to assume this regularity, omega-1 and omega-2 flat as right A modules, then you get that generalization of this notion of PDE, so formally integrable PDE in a generalization of the Spencer, Quillen, and Goldschmidt sense. These will correspond precisely to objects in this Eilenberg-Moore category. And this is some category which is canonically associated to any comonad, in our case, the jet comonad, and the morphisms will be Cartan distribution preserving maps. So this gives some notion of PDE in the non-commutative setting. We've seen examples. So the 2-jet would be a first order PDE in this sense. If you have any sort of differential operator in our sense, its kernel will be a differential equation in these terms. But I don't know, this is very early on. So like, what is the notion of differential equation in non-commutative setting? It's now there is a notion which makes sense in that it generalizes the classical setting, but beyond that, I don't know, we need to look at more examples and try to understand this in more detail. And I guess I should wrap up there. So thanks for your attention.
This notion of differential operators brought it for community
Just successive bracketing.
Yes.
Yeah. Yeah. I mean, so this generalizes that, but it's not going to be successive bracketing in general. You can't just do commutators because, I don't know, that's sort of well, it's not commutative. It's something that only works in the commutative setting. In general, it won't. We would hope that in the quantum group setting, you would have some sort of Q commutator, but we haven't checked this yet. Yeah. I would expect it not to hold in general. Maybe for some specific examples like quantum groups, maybe there it's a Q commutator. I mean, if you look at classical differential geometry, yes, these things coincide. Like differential operators you get from successive bracketing is precisely the differential operators from jets. If you want to do it for general commutative algebras, There's this Georgian guy, Sardanashvili, who sort of generalized differential operators, worked with it in that setting, related it to jets there. And he tried to move into the non-commutative setting, but he was essentially trying to do the same thing, like still having iterated brackets. And it seems like that was where he ran into difficulty. Sardanashvili? I don't remember his first name, but Sardanashvili. His last name.
Yes, so we seem to have some examples.
Yes, agreed. So we're talking, yeah. So we're talking to Ray and Ale about this, and it would be nice to have, what we've talked about with Thomas.
It does